Okay guys, this is Unit 9, Video 2 on sound and the Doppler effect. Alright, so here we go. So today, after this lecture, you should be able to solve for wave speed and frequency of sound waves, relate frequency to pitch and amplitude to loudness, and solve for the frequency of a moving sound source. There are going to be some demos that we're going to do in class on the Doppler effect, so we're just going to get through like the basic math, and then we'll talk more about the actual conceptual background of the Doppler effect when we're in class. Okay, so let's recall from last lecture the difference between a transverse and a longitudinal wave. Remember, transverse means the particles move perpendicular to the wave, and in a longitudinal wave, the particles move parallel to the wave. So basically, transverse is the one that's sort of like wavy, like that, right? And then longitudinal is the one where it was like, it's like compressed, and then more like expanded, and then compressed, and then more expanded. So since we're talking about sound waves, those are going to be longitudinal waves, okay? Draw a picture that clearly demonstrates amplitude, period, frequency, and wavelength. So I'm just going to draw a wave here. So amplitude is the distance from the equilibrium point to the max or the min. Those are both the amplitude, okay? The wavelength is the distance from one crest to the next crest, or one wave, one full wave. So it could be from the crest to the crest, it could be from the trough to the trough, it could be from, this point, to that point, which is exactly the same distance. Okay, so one full wave. All right, and then period and frequency. So I'm going to draw this a little bit differently. So the period is the time for one cycle. So t equals time for one cycle. So from crest to crest. And frequency, if we like maybe draw it from here to here, frequency is the number of cycles per 1 second. Okay, and remember that period and frequency are inversely proportional. Relationship between frequency and period. So I just did that. That's t is 1 over f, or f is 1 over t. Same thing. Wavelength and velocity. Well, velocity is frequency times the wavelength. And then wavelength and period. If you sub in 1 over t for frequency, then you can create this equation. And then if you sort of move everything around, you can get t equals wavelength over velocity. Probably won't use this very much, but it's there in case you need it, okay? Now, this next chunk on your notes is just like some wave basics, all right? This is just like some facts and stuff about waves, and sort of like just kind of a culmination summary of waves. So I'm not going to read through that right now, but those are some notes that you should maybe read through when we're done with the lecture. Some of this is stuff that we've talked about. Some of it's just some other stuff. This is just like a demo online that you can watch. It's my dog moving around. Anyway, so you can get through this, all right? So let's go through an example based on the stuff we did last time, okay? So elephants can hear frequencies at low of 20 hertz, that should say. I don't know. At low of 20 hertz. Sorry about that. What is the wavelength of that wave? So we know that sound waves in air travel at 343. We assume air is about 20 degrees Celsius. And so if we know the frequency is 20 hertz, then we're looking for wavelength. We use this equation. So we have 343 equals 20 wavelength. And if you divide, you get the wavelength equals 17.2 meters. Okay. Second example, if middle C has a frequency of 440 hertz, what is the wavelength? Same idea. Okay, we'll assume that it's at room temperature in air, if unless they tell us otherwise. So we'll assume 343 equals 440 times the wavelength, and if we solve for wavelength, you get 0.78 meters. Okay, so that's what we did last time. All right, let's flip to the next page. So this will be the new stuff here. So sound waves are caused by vibrations. Okay, so when you speak, your vocal cords vibrate the air, and the vibrating air is what makes sound. So a tuning fork is a specially shaped piece of metal that vibrates at a specific frequency. The prongs hit the surrounding air molecules, causing noise. So I'll actually show you one of these in class, but basically if you take a piece of wood or a piece of metal and you hit this thing, it makes a little noise, all right? Because basically they just vibrate, which vibrate the air around them, and it makes noise. Speakers and frequency generators a speaker is a cone-shaped membrane with an electromagnet that causes it to vibrate quickly. So really all that speakers are just basically electromagnets that vibrate really fast, and those vibrations cause sound, okay? This is a little note I put in here just so that you sort of understand. So when we talk about pitch or volume, pitch would correspond to the frequency. So the higher the frequency, the higher pitch the sound is going to be. And then the higher the amplitude, the higher the volume. Okay, so that's how those correspond. All right. Waves can be added or subtracted. When they hit each other, they make a resultant wave. So we have this stuff called interference, meaning that what happens when two waves come in contact with each other. Okay, and so we have constructive interference and we have destructive interference. Constructive means that two waves that are sort of lined up so that they're at their crest at the same time and their troughs are at the same time, those will interfere constructively, okay? And so what happens is they basically add up. And so you have an amplitude here, let's say it's 2, and an amplitude here of 2. They'll make a new wave with an amplitude of 4. And so it will get bigger, okay? Yeah, so destructive interference is the opposite. So if you have a wave like that, and now it lines up with a wave that is, sorry, all that little clicking is just my dog walking around the hardwood here. Anyway, so if you have a crest and a trough lineup, right, crest and trough lineup, they cancel each other out. So this is assuming that this is 2 and this is -2, right? Or they both have an amplitude of 2. Let's say that this one has an amplitude of 2 and this has an amplitude of 1. Then you're going to get, +2, -1, and you're going to get +1. So you'll get like a little wave, right, with a lower amplitude. But in this case, we're going to say that they're both equal. And so what you get is just a flat line, and the waves would actually cancel each other out. Okay? Now, this is actually how your noise-canceling headphones work. Your noise-canceling headphones have a little receiver inside the device, and they can see what frequencies are coming in and what amplitude the waves are that are coming in. And then it basically sends out a wave that's the exact opposite and cancels those sounds out. And that's how those work. Okay? Okay, sorry. So I had to feed the dog here. So now complete the following diagram and write a sentence explaining how the headphones work. Okay, so there's going to be outside noise. Let's say that the wave comes in like this. Okay? The headphone speaker is going to send out a wave exact opposite. Okay? And the resultant wave will just be flat. And so that's how it cancels it. They can't detect every single frequency coming in and send back ones that are exactly opposite of every single wave. So noise-canceling headphones do a really good job, but they don't do a perfect job. Okay, so some sounds are still going to get through. It's not going to be, 100%, but that's how they work, is they use this destructive interference to cancel sounds out, or at least make them lower, okay? Now, the Doppler effect is totally different, totally unrelated, okay? The Doppler effect is something that you guys have definitely heard of, or you've witnessed, but you have not maybe known what it was called, or maybe you did. The Doppler effect is the result of moving sound sources. Okay, so think about it as a sound source catching up to or running away from other sound waves, and this will cause a shift in the frequency of the sound. Frequency is pitch, okay, not loudness, pitch. So if you've ever noticed that, like, when a siren goes by you, right, like as it approaches you, it has like sort of a high pitch, like, sound, and then as it goes away, it sounds different. It sounds like a lower pitch, and we're actually going to listen to these in class and sort of talk about why that happens and more conceptually, but I'm going to get through the math here. So it shifts frequency, okay? And when it does that, we hear it. To solve for problems that involve moving sound sources and or a moving observer. So it doesn't just have to be that the sound is moving, it could also be that you're moving. So it could be that you're standing still and a car drives by you while it honks its horn, you would hear this effect. If you were running, let's say a car was sitting at rest and you were running toward a car that was honking its horn, you would also hear this effect, okay? Or you could have both things moving. You would be the observer and then the car would be the source of the sound. And if both of you were moving, you would hear this effect, unless you're moving at the same speed in the same direction. And then it would be relatively, you would just hear like whatever sound it's giving off, okay? All right, so the equation we use to solve for Doppler effect is a little weird and a little complicated, all right? So frequency of the observer, or observed frequency, okay? Plane V is velocity of sound. VO is the velocity of the observer, okay? On the bottom is velocity of sound. And then V, velocity of the source, so whatever's making the sound. And then times the, oops, let's not run into this here. Times the frequency of the source. Okay, so I'm going to put this list over here so that you know what these stand for. So FO is observed frequency, okay. Then you have V, which is speed of sound. So most of the time that's going to be 343 because it's usually in air, okay. VO is velocity of observer. Vs is velocity of source, and then Fs is the frequency of the source. So like actual frequency of the sound, okay? Now, the signs are really the part that trick people, okay? So here's sort of the way that I do it. So the units are going to be hertz because that's how we measure frequency. Here's how we do the signs, okay? And this is, I think, the easiest way to remember. So these are the signs that come with the equation. There's a plus on top and a minus on the bottom, okay? Now, if the observer is moving toward the sound, you would make this a positive velocity, which would leave this positive, okay? If the observer, person who's listening, is moving away from the sound, you would make this negative in front of here. So you'd make this velocity negative, which would turn this sign into a negative sign. Okay? Same rules for the source. If the source is moving toward the observer, the source of the sound is moving toward the observer, there's a little plus in front of this, which just leaves this sign exactly how it is. A minus and a plus makes a minus. If the source is moving away from the observer, you put a minus sign. 2 minus signs makes a positive. Okay? So toward is positive. Away is negative. Now here's the problem that the mistake people make. Toward is positive. So people think like, oh, the source is moving toward the observer. Okay, cool, so I'll make this sign positive. No, you're not changing the sign in the equation. You're putting a little positive in front of this here. Well, minus a positive number is still minus. Okay? If it's moving away, you'd put a negative here. A negative and a negative make a positive. So that's when the sign changes. So that's where it gets kind of tricky, is these signs are attached to these velocities. And you know what, maybe it would make better sense to put an extra parenthesis here so that you know that you're going to have to decide on the sign of that and then sort of play with the signs. Okay, so we're going to go through a couple examples, but that's where the main mistake comes from. So you really need to focus on making sure that you've got those signs down, and ask me when you get confused about how we're supposed to do the signs, okay? Okay, so I'm going to zoom in here and let's do an example. All right, so a train moving at a speed of 40 meters per second sounds its whistle, okay? So the train is sounding the whistle, so the train is the source, all right? And so it's moving, so the velocity of the source is moving 40 meters per second, okay? with a frequency of 500. That's the source. That's the source frequency. That's the frequency of the whistle. Okay. Determine the frequency heard. That's the frequency observed. Okay. By a stationary observer, that means that it's not moving. So the velocity of the observer is 0. As the train approaches the observer. So here's the train. Okay. It's driving toward a person standing still. Excuse me. Okay. Now, we're assuming, unless you're told otherwise, that the velocity of sound is 343 in air. Okay? So let's make sure we have the signs correct on these velocities before we plug them in. So the person that's observing or hearing the sound is not moving, so there's no sign associated with that. Okay, so we leave that alone. Just leave it positive or 0. The source is moving toward, the train approaches the observer, moving toward the person. So that means that this 40 meters per second is a positive 40 meters per second. Okay? So when we plug it in, we'll plug it in that way. So we have FO, which is what we're looking for. We have 343, okay, that's this, plus the velocity of the observer is 0, divided by 343, minus positive 40. Okay? And you can put the positive, but positive 40 is positive 40. Okay? The minus does not change to a positive because that's part of the equation. So it's just minus positive 40. Okay? Times the frequency of the source, which is 500. Okay? And then we just plug in, or we just, plug into our calculator. All right? And if you do that, you end up with an observed frequency of 566 hertz. Now, here's how you check if your answer makes sense. Anytime the source, the sound, is moving toward the observer, or the observer is moving toward the sound, they're getting closer together, you should hear a higher frequency than is actually being emitted. Anytime they are moving away from each other, you should hear a lower frequency than is emitted. So if this frequency is higher than that one, the observed frequency, the one they hear, is higher than that one, then you know that they must be approaching each other. And in this case, we know they're approaching, so that makes sense. Okay, so that's sort of how you check your answer. That's how you figure out if you made a sign error. Okay? All right, let's do another example here. An ambulance travels down a highway at a speed of 33 meters per second. Its siren is emitting a sound. So the ambulance is the source. Okay, and it's moving at 33.5 meters per second. And it's emitting a sound at a frequency of 400 hertz. Okay, that should say S. Sorry, that looks weird. Okay. What frequency is heard by a passenger in a car traveling at 24.6 meters per second in the opposite direction as the ambulance? This should say ambulance. Okay. So the velocity of the observer is 24.6. So they're saying what frequency is heard. That's the observed frequency. By a person traveling in a car going this speed, okay, in the opposite direction of the ambulance. Now, in this case, they're saying it approaches, okay? So here's the ambulance going this way, and then here's the car approaching it. So they're both going toward each other, okay? So when we set this up, they're going toward each other, so both these velocities are positive. So you can just leave them both positive. So when we plug in the signs in the equation, we'll just stay how they are. So we have FO is equal to 343 plus the observed velocity, which is 24.6, divided by 343 minus 33.5 times 400. Okay? So the signs just stay the same because these were both positive numbers. Okay? And if you solve for that, you get the observed frequency of 475 hertz. Now let's check and make sure that makes sense. They were approaching each other. The actual frequency was 400. The person in the car hears 475. That's higher, and they're approaching, so that makes sense. Okay? Now let's go moves away from them. Okay? So now they've passed each other, and now we have the car going one way and the ambulance going the other way. All right? They're going away from each other. So now all that changes is that the source is now negative 33.5, because it's going away from the car. Frequency is still 400. The observed velocity is now negative 24.6 because the car is also going away from the ambulance. Okay, and we're looking for FO. Now, just as a side note here, they're both going away from each other. If this guy was going this way and this guy was going this way, this guy's going away, so it'd be negative. This guy's going toward, so it'd be positive. Okay? So it's not just because like, oh, well, they're, in total, this guy's going away. No, this guy's going away, so it's negative. This guy's going toward, so it's positive. Okay? But in this case, they're both going away, so we're not going to deal with that. All right, so they're both negative, so we plug in 343. Now the velocity, oh, this was a positive sign up here before. It's now negative 24.6, okay? Down here at 343, this was a negative sign before. It's now negative 33.5. It's 400. So if we fix these signs now, or adjust them here, we get 343 minus 24.6 over 343 plus 33.5. And if you solve for that, FO, you get 338 hertz. Now, let's make sure it makes sense. This is the frequency that we're hearing. It's lower, meaning it's a lower pitch, than the frequency that's actually being emitted. But they're going away from each other, so it should be lower. So that makes sense. Okay? So this is like kind of mathy. It's not crazy hard math. It's just that there's sign errors and things. So just be careful. Make sure you make a list of variables. Okay, I'm going to look for this on your test when we test on this. You need a list of variables. Okay, I'm not trying even to solve this problem without a list of variables, just because there's too many. All right, so just be careful with that. And then if they were to tell you like, oh, that this is in underwater and sound moves at 1500 meters per second underwater, then instead of 343, you'd put 1500. All right, that's the only difference. But we will do some conceptual examples so you guys can actually hear this effect. You know what I'm talking about. You've definitely heard it before, but I want to show you some examples, and then we have a little video on the Big Bang Theory about this that we'll watch. Okay? All right, you're all set.